This lecture corresponds to section 17.2 of the openstax astronomy text. The material here will show you how to compare the relative temperatures of stars based on their colors, and it will help you to understand how astronomers use color indices to measure the temperatures of stars. Measuring a star's surface temperature is easier than measuring luminosity because temperature doesn't change with distance. We determine surface temperature from either the star's color or its spectrum. The last time you were out on a clear night, you may have noticed that the stars appear to be different colors. Perhaps you've seen the constellation Orion and noticed that this star, Betelgeuse, appears red-orange compared to this star, Bellatrix, which looks more blue. Stars appear in different colors because they emit thermal radiation. A hot star like Bellatrix emits more blue light, and a cooler star like Betelgeuse emits more red light. Astronomers can measure surface temperature by comparing a star's apparent brightness in two different colors of light. For example, consider the hot star Vega. Imagine we have two filters. One only lets through blue light. We'll call it the B filter. And the other only lets through yellow light. We'll call this one the visual or the V filter. Vega is a hot star, and it emits more blue light than yellow. Therefore, if we compare the amount of light from Vega that makes it through the blue filter with the amount of light from Vega that makes it through the yellow filter, we'll definitely see more light in the blue. What astronomers actually do is count the number of photons coming through each filter and then subtract one filter from the other to get what is called a color index. In this case, we're taking the number of photons in the blue filter and subtracting off the number of photons in the visual or the yellow filter to get a B minus V color index. A hot star will have more blue filter photons, and a cool star will have more yellow filter photons. Astronomers use a variety of different colored filters, but the wavelengths of light that a particular filter lets through is standardized. Every B filter, for example, transmits wavelengths near 420 nanometers. A visual V filter or an ultraviolet U filter will also have a specific and standard wavelength transmission. This way, astronomers can agree on how the color indices correspond to actual temperatures. A star's spectrum provides a second and more accurate way to measure surface temperature. If you were to study the spectra for many different types of stars, you would see that the spectrum for a hot star looks different from the spectrum of a cool star. The type of spectral lines present in a star spectrum can provide us a direct measure of the star's surface temperature. We classify stars according to surface temperature by assigning a spectral type determined from the spectral lines present. The hottest stars with the bluest colors are called spectral type O. The next hottest stars are spectral type B, the next hottest are A, followed by F, G, K, and M, with spectral type M being the coolest on this scale. There are several mnemonics for remembering spectral types, and here is one of them. Each spectral type is divided into 10 subcategories. A spectral type O0 star is hotter than an O1, which is hotter than an O9. The O9 star is hotter than the B0 star, and so on. The coolest on this scale is M9. Our sun is a type G2 star, hotter than a G3, but cooler than a G1. Here are actual stellar spectra for stars at different temperatures. We can see the hot O star has weak hydrogen lines because the surface temperature is so high that nearly all the hydrogen is ionized. This means there's no electron to jump between energy levels to create the hydrogen absorption lines. Stars displaying lines of molecules like this M star must be cool because otherwise the molecules would have broken apart. Now, I know that the spectral type letters may seem a little random. The ordering of O, B, A, F, G, K, M actually stems from work that was done primarily by women at the Harvard Observatory in the early 1900s. And I have a whole other lecture about this topic. Stars can have surface temperatures ranging from about 3,000 Kelvin to about 40,000 Kelvin. And remember, Kelvin is a temperature scale just like Celsius or Fahrenheit. We observe that cool red stars are much more common in our universe than hot blue stars. Later in the semester, we'll discuss why this is the case. That's all for now. Take care, and I'll talk to you again soon.